Welcome to the deep dive, where we cut through the noise and get straight to the insights you need. Picture this with me. You're settled in the cockpit, the engine awakens with a powerful surge, and you climb, tracing an invisible path upwards into the vast open sky.
Ah, that feeling. There's really nothing quite like it.
That feeling of ascent, of defying gravity, is truly exhilarating. But behind that thrill is the mechanical heart of your aircraft, the engine. And truly understanding how that heart beats, especially as the air things around you, isn't just about passing an exam, it's absolutely fundamental to mastering flight.
Couldn't agree more. It's foundational knowledge.
For you, our dedicated ATPL student, those crucial exams loom large, and grappling with complex systems like piston engine power augmentation is more than just another topic on the syllabus. It's about building a rock-solid foundation of knowledge.
Exactly. And these systems, superchargers, turbochargers, they can seem a bit daunting at first.
That's why this deep dive is custom-tailored to untangle the intricacies of superchargers and turbochargers, providing you with the critical understanding to excel. Our mission today is clear. We're cutting through the complexities, stripping away the jargon, and delivering focused, actionable insights that will make these abstract concepts truly click.
We want to make it stick.
Today, we're embarking on a journey to unpack how piston engines perform at different altitudes, exploring precisely why they lose power, and then revealing the ingenious solutions aviation engineers develop to counteract this natural phenomenon.
Right, how we fight back against physics, essentially.
We'll specifically zero in on the fundamental differences between internally driven superchargers and externally driven turbochargers, their intricate control systems, and how they ultimately impact engine performance.
Two very different beasts, even though they achieve similar goals.
Along the way, we're going to explicitly answer some of those trickier questions you might face, like what a manifold pressure gauge really measures, how an automatic boost control unit works its magic, the core role of a turbocharger, and what actually drives it, and how to interpret those sometimes confusing altitude power curves.
Key points for any ATPL student, definitely.
And as always, we'll give you a clear, concise summary at the end to cement all that vital learning. So, let's get started. Imagine you're climbing into the blue. What happens to your engine's power? It's not just a simple linear decrease, is it?
That's right. And understanding the why behind that atmospheric change is absolutely key to appreciating how these systems augment engine performance. What's truly fascinating here is how engineers found ways to seemingly defy the natural drop in air density with altitude, enabling aircraft to perform efficiently higher and higher.
Okay, to really get why supercharging is such a big deal, we need to start at square one. How does a basic piston engine actually make power? What's the absolute core determinant?
Well, at its heart, the power an engine produces fundamentally relies on the weight of the mixture, that's the fuel and air mix, that it can effectively burn in the cylinders within a certain time frame.
The weight, not just the volume.
Exactly, the weight. Think of it simply. The more oxygen molecules you can pack into each cylinder, which means a greater weight of air, the more fuel you can efficiently ignite. More efficient ignition means more energy released, and that translates directly to more power.
So it's all about cramming in as much oxygen-rich air as possible.
Precisely. Getting that dense, heavy charge into the combustion chamber is the name of the game.
And this weight of mixture thing, it's directly tied to air density, which, well, changes all the time, doesn't it?
Absolutely. Air density is the key variable here, and that density, in turn, critically depends on two things: the air's pressure and its temperature, specifically within the induction manifold.
Right.
So as the air becomes less dense, maybe because you're climbing higher or it's just a hot day, you literally have fewer air molecules packed into the same volume. That means less oxygen available for combustion.
And less oxygen means?
Less fuel can be burned effectively, which directly translates to a significant drop in power output. It's an unavoidable consequence of physics, really.
Can you give us an analogy for that?
Sure. Imagine trying to, say, run a marathon at the top of a high mountain versus doing it down at sea level. Your lungs, or in this case, the engine, simply can't pull in enough.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.